However, Newton's law of universal gravitation isn't actually a universal law.
If you've heard of it, you've probably seen a picture like this, or a demo like this. Lies! All lies!
And one of the coolest ideas is the idea that gravity might inhabit extra dimensions.
This is the standard bent sheet analogy for curved spacetime, but I think this demo is misleading.
In 1905, Einstein gave us the equation for mass-energy equivalence. In 1915, he gave us his theory of special and general relativity. 100 years later, and we're still struggling with the things these theories have taught us about our world, the universe, and reality. These theories taught us that everything is made of energy, that time is relative, that nothing can exceed the speed of light, and that gravity, which we think of often as a force, is actually an effect from the curve of space and relativity coming together into what we now call space-time. All of these ideas Einstein showed the world were on top of the fact that the previous few decades, so around the late 1800s, we were already beginning to discover the world of quantum mechanics. This is the world of atoms, electrons, subatomic particles, electromagnetic waves. And this gave to us a new way to look at our world because we started to realize that everything around us is mostly empty space with teeny tiny little particles pushing and pulling against each other, which is a mind-blowing idea. But the pinnacle of our consternation is the fact that the math that we have for general relativity and quantum mechanics both seem to do a great job at describing the world around us, but they don't get along. While general relativity helps us understand gravity and it helps us understand relative time, we don't see gravity in quantum mechanics, and quantum mechanics is struggling to help us understand where gravity comes from. Because our thinking is quantum mechanics should at some level explain everything. And even though these theories don't seem to get along, the truth is they influence each other. Our first hope at making sense of these two theories came from a colleague of Albert Einstein. His name was Theodore Kaluza. He proposed in 1921 that the implication of general relativity, as Einstein laid it out, is that our world isn't 4 dimensions. And when I say 4, I mean 3 plus 1. Length, width, height, and we have time. And the reason we say plus 1 is because time is weird and we don't seem to understand it as a dimension. Kaluza proposed that we have, in fact, 5 dimensions. Maybe best represented as 4 plus 1. That idea was so promising, Einstein told him, at first glance, I like your idea enormously. While the math seemed promising, the biggest objection at the time to Kaluza's idea of 5 dimensions is that, okay, if there is 5 dimensions, where is it? Great question. In 1926, Oscar Klein offered an answer. Maybe the 5th dimension is there, but it's very, very small. It's a quantum dimension. This became what we know today as the Kaluza-Klein theory. The idea of quantum dimensions that are really, really small, hung around in theoretical physics with a kind of cult following. The more popular version of this idea today is string theory, which postulates not 5 dimensions, but 10, 11, or even as high as 27 dimensions. Again, there is a lot of promising math behind these ideas, but the question remains, where is it? Because we can't test it if we can't see it, if we can't observe it. How do we know they're there other than just, hey, the math kind of fits? So this is what I'm going to talk about today. I would like to propose a different way of thinking about dimensions and space itself so that we can finally observe, identify, test, and understand extra dimensions. For this video, though, I'm going to be focusing on that 5th dimension. And after giving this a lot of thought, I believe the reason we have gone for over 100 years since Einstein without being able to understand where this extra dimension is or be able to make any progress on this comes down to one image, one single idea that has been pounded into our brains ever since this started. You learn it in school, you see it on YouTube, it's everywhere. And it's the idea somewhat similar to a bowling ball on a trampoline, or a little bit like this. Before we dive in, let me talk a little bit about what to expect from this video. I am focusing the first half of this video on concepts I think everyone can follow along with. And then the second half of the video is going to dive more into the math and the evidence. I have put chapter markers and descriptions so that wherever you find yourself at your level of science, you can kind of skip around and watch this video as you feel like you prefer to. For those of you who are here for the clickbait thumbnail, yes, I really am going to talk about how you can perceive 5 dimensions. However, it is also my intention to make this video a pitch for a real scientific theory, which I hope can fill in the gaps between quantum mechanics and general relativity. I call it the unifying theory of dimensional geometry and interaction, or the universe is a really weird shape. All that said, I do have to start somewhere. I am assuming that you're watching this video with a basic knowledge of general relativity and quantum mechanics, enough that you kind of already know the conflicts between the two. If that's not you, but you're still interested in this video, I have included below in the description links to different content creators on YouTube who explain the ideas of general relativity and quantum mechanics, I believe, in a very accessible way. There are some great content creators on YouTube when it comes to science, and the people I've linked to below not only do a great job, they're often very fun, but most of all, they're very accurate in what they present. And I'll just want to take a minute to give a shout out to a few of my favorites. Sabine Hassenfelder, I hope I'm saying that right, probably the most sane voice in physics right now. Parth G does excellent math tutorials when it comes to relativity and quantum mechanics and many things. Also is the person who has personally made me realize that the plural of math is maths, and no one can convince me otherwise at this point. Maths. It's just fun to say. 3 Blue, 1 Brown, great place to go for any math tutorials. Minute Physics also does a great job with stick figures and fun illustrations. The Science Asylum is probably I'm pretty sure he's going for the next Bill Nye the Science Guy, and he does a pretty good job at it. And Dr. Don Lincoln from Fermilab, also a great job at helping you understand where we really are, what we understand, what we don't. These are all great content creators. And while I recommend these channels, I do want to make it clear I haven't spoken to any of these people before doing this video. I have no idea if any of them would even want to be associated with this or me personally. So don't assume just because I'm recommending them that there's any endorsement or anything here. So that being said, now that you're all caught up, we're going to dive into it, and I hope you enjoy. In 1884, Edwin Abbott wrote the book Flatland. In this book, creatures live in a two-dimensional world, identified by shapes, circles, squares. And during the book, they interact with creatures from 1 dimension and creatures from 3 dimensions. And while he originally wrote this book to be a social commentary, the book also opened up our imagination into thinking about what it would be like to experience objects or phenomenon from extra dimensions in our reality. In 1980, Carl Sagan did a bit on 4 dimensions in his show Cosmos on PBS. That segment inspired me a lot, which is part of the reason why I started going down this rabbit hole. By breaking down these ideas and having them in our minds as we move forward, it'll make it easier to understand how we can perceive these extra dimensions. So let's start with the simplest idea. And that idea is that each dimension stacks on the other. So you have 1 dimension, you have a line. 2 dimensions, we take that line, we stack it up, we get a square. We take those squares, we stack them up. How do we stack a cube? This is how most people tend to draw a tesseract, or the idea of a fourth dimensional cube. It's basically kind of like a cube inside of a cube, just with a lot more lines. I have a better solution to this, but we won't get into that right now. Just keep that image in your head for the moment. Concept number 2. Distance and size change with dimensional perspective. For example, two objects can be right next to each other in 2 dimensions, and yet in 3 dimensions, they're actually extremely far apart. People like playing with this on Instagram all the time by taking pictures of them pinching the Eiffel Tower in their fingers. Concept number 3. Higher dimension objects can only be observed in lower dimensions through relative motion. This one starts getting tricky. Let me explain. If I live in a 2-dimensional world, a flat land, and a 3-dimensional object, let's say a ball, comes through my world, that ball is going to appear out of nowhere as a dot. It's going to grow into a circle, and then that circle is going to shrink, and it's going to disappear. Now, the only way I have any ability to tell how big that object was, or understand the shape of it, is by how it changes over time. Concept number 4. We could perceive multiple objects in a lower dimension that are actually a single object in a higher dimension. And the only way we know that those multiple objects in a lower dimension are actually one object is if interacting with one of the objects affects the other. This concept alone can explain some of the strange behaviors that we see in quantum mechanics. I won't go into it now. We'll get to that later. Entanglement. Concept number 5. Dimensions can be experienced as objects or in space. And here's what I mean by that. When we try to think of multidimensional objects, we often try to think of, cubes and tesseracts, objects. But a dimension can also be space. It can be something that you're inside of. So when we're thinking about dimensions, let's keep in mind that we can experience something from an extra dimension as an object, but also as space we are inside of. And that's going to be important as we move forward. Concept number 6. A dimension can be limited, but still be everywhere at once. Now, this is one of the hardest things for people to get, so I'm going to try really hard here to make it easy. We live in a 3-dimensional world, and at least as far as we're normally aware, those 3 dimensions are infinite. The universe seems to infinitely go this way and this way and this way. As far as we can tell, it just keeps going. Well, think about if you lived in a 2-dimensional world. You would still think the universe was infinite because the 2 dimensions that you interact with every day go on forever. But what if you took a 2-dimensional world and added just a little bit of a 3rd dimension? I call this the ant farm dimension. To the most part, the ants kind of just have 2 dimensions, but that 3rd dimension is really small, like maybe an inch. To the ants' point of view, they wouldn't think of that 3rd dimension as a dimension. They would do kind of what we do with time. They wouldn't think of their world as 3-dimensional. They would think of it as 2 plus 1, because the rules for that 3rd dimension are different than it is for the other 2. It's short. All right, concept number 7, and here's where we're getting really deep. The total energy of a closed system, if distributed equally across all dimensions, each dimension will contain exponentially less energy. You could also see this in stunts. A stuntman falling off a building, that's a straight down 1-dimensional force, body, floor. By adding a mat outside of it, that force becomes distributed across a large 3-dimensional surface. So this idea of how force gets concentrated as you go lower and lower in dimensions, but spread out the more dimensions you express that force in, is very important to remember. And I'm just going to jump to one thing right off the bat. That's how a nuclear bomb works. I mean, the whole reason E equals mc squared is a reality, and that we can take something as teeny tiny as a hydrogen atom and break it apart and get devastating, citywide destructive force, is because force that is being expressed over many, many dimensions, all of a sudden becomes expressed only in R3. And when that happens, it's a lot worse. And those are 7-dimensional concepts. All right, so we're getting to the good stuff, but we still need to take a minute and talk about some misconceptions on gravity. Remember when we talked about the bowling ball on a trampoline earlier? No, we already went through that. People love this analogy for gravity because it feels good. It's most people's first introduction to the idea of curved space-time. Both show a round thing going around a round thing. It's familiar. While all physicists agree, it is a rough illustration of what's going on with gravity. The deeper problem is that it is completely backwards. Space-time doesn't form a vortex at all. That is a fundamental misinterpretation of general relativity. Instead of a bowling ball on a trampoline, a more accurate analogy would be a bowling ball in Jello. Wait, no, sorry. More like a bowling ball in a box of Jello. So no matter what level of familiarity you have with general relativity, your reaction at this point probably ranges from a stern eyebrow raise to possibly yelling at the screen. Well, good. You should be skeptical, but don't worry, I brought receipts. If you ask most people to describe gravity, they probably say something like this. Gravity is the force that pulls us down. Or more sciencey people might say, gravity is a force that causes objects with mass to attract one another. Both these statements are almost completely wrong.
Amazing. Every word of what you just said was wrong.
Gravity is not a force, it's an effect. This is not my opinion. This is the point. This is the meaning of general relativity. So let me pause to say that there's a lot about gravity and general relativity that gets misunderstood, lost, or forgotten in these discussions. We are going to take a minute to review what general relativity taught us regarding our misconceptions of gravity. I want to make it clear at this point that this is not a part of my theory, this is not my opinion. There will be a label at the bottom of the screen so that you know at what point I'm switching from just talking about things that the science community already knows to when I'm getting into the stuff I'm proposing. So as crazy as these next few things may seem, just know. All right, so misconception number 1. Like I said, gravity is not a force. Gravity is actually a phenomenon produced by 2 main effects. The first one is time dilation. Most of what we call gravity is actually the effect of time moving slower in a gravitational field. Think of a rowboat, where a person on one side is a lot weaker than the person on the other. This unequal motion on both sides of the boat represents a lot of what happens when things enter into an orbit or gravitational field. They start turning as one part starts going slower than the other. That's what causes that kind of pull effect. The next thing that causes what we feel as gravity is the curve of space-time. So the time dilation I'm referring to, that's not an on-off switch. The way that works is it's more like a gradient, meaning that the closer you are to the center of gravity, the more time slows down. So because of that gradient, that creates something that in general relativity we call geodesics. And it requires a lot of math. It's a lot of what this equation here for general relativity is about. So those 2 phenomena together, time dilation and the curve of space-time, that's what actually causes gravity. Now again, if you're struggling with this idea, I will have references below in the description so you can see people that just spend a whole lot of time just on this one thing. We fall towards the Earth. Well, that's wrong. I mean, it's what we experience, it's what we see, but again, according to general relativity and what we've learned about physics, it's actually not accurate. Basically, what you feel as gravity when you are standing on the ground is not because you are being pulled down to the Earth. It's because the Earth is accelerating up towards you. One of the best ways to experience and understand this is to to take a scale, like to measure your weight into an elevator, you will notice that as the elevator accelerates up, your weight will increase. Likewise, if an elevator is going down and you're in the elevator, you will get lighter for a bit as the elevator accelerates downward. While your mass stays consistent, weight is a consequence of accelerating force. It's basically a measurement of how much one thing is pushing on another. Now, I don't want to spend too much time on this concept, but I know it can be a difficult one. So if this is new to you, Veritasium has done a great video on this, really thorough explanation, and I have also linked to it in the description. The reason I want to highlight this concept is because it raises a mind-tingling question. How is it the Earth is always accelerating outward without getting bigger? It's just hard to picture. So the technical answer, or the current answer, is with gravity, it's causing space to kind of turn in towards the Earth. But we're not actually moving, it's space that's changed. So in order for us to stay still, the Earth has to be pushing against us to keep us in place. That's how you can start to answer that question. How is the Earth accelerating without getting bigger? So that explanation is mathematically sound, but just because the math works doesn't mean we know why it works. Conceptually, there is a problem here that has always troubled me. First, there is a big chicken and egg problem. Newton's third law states for every action, there is an equal and opposite reaction. So we know that one of these effects, the curve of space-time, or the acceleration of the Earth, one of them has to cause the other. So which one is it? Is it the Earth accelerating, or is it the curve of space-time that's causing the other effect? That's an interesting one we're going to get into a little bit later. Second, this is still the only case in nature we have something accelerating, but not moving visibly in three-dimensional space. Yeah, I know, I said space-time is curved. Curved where? Misconception number 3. The speed of light is constant. All right, hold on. Before you throw tomatoes at the screen, hear me out. One of the foundations for both general relativity and quantum mechanics is that the speed of light is constant. This is also one of the most miscommunicated principles in physics. So, first of all, it's not the speed of light that's constant. The constant is actually the speed of causality, which is a better representation of the c in E equals mc squared. It limits speed, but it also limits things like vibration, voltage, or how hot something can get. That c it's a limit to many things. Almost any time there's energy, c is there as a limit. Light itself, just normal light, can actually be slowed down in a variety of ways. We know that we can slow it down by shining it through different substances. It's more accurate to say that c is the speed limit for light. As a matter of fact, without it, light, for all we know, could have an infinite speed limit. Second, even c is not constant in all frames of reference in general relativity. Okay, it's true. There is one time, one situation, one circumstance where we observe c changing. And that is when light, or for that matter anything, travels through a gravitational field. Many of you have probably seen the videos which explain how light is always observed traveling the same speed regardless of your frame of reference. If not, I've also linked to that in the description. This, however, is true for special relativity, not general relativity. And it's not that these two things conflict with each other, it's just that general relativity is covering more circumstances than special relativity, especially in regards to gravity. So here's how it works. Let's say I have two spaceships out in space. They're not near any gravitational field, just enjoying the dark, deadly, cold, soulless void of space. Now, if one spaceship shines a light at the other spaceship, that light is going to travel in a straight line and it's going to go the full speed of c. However, if we take these two spaceships, leave them the same distance apart, but now we're going to put Earth's gravitational field between them. When the first spaceship shines that light to the frame of reference of the second spaceship, that light is going to slow down, redshift, and bend a little bit as it comes. And what that does is it means that the second spaceship is going to see the light from the first spaceship a little farther out than what it actually is. And we call that gravitational lensing. All right, so all three of these misconceptions, all three of these ideas are critically important to getting to our next chapter, which we're going to now finally talk about the fifth dimension. Okay, now we're going to take everything that we've covered from the dimensional concepts, along with those weird realities of gravity that we covered with the misconceptions, and we're going to put them together to reveal a fifth dimension of physics. You'll notice I said a fifth dimension, not the fifth dimension, and here's why. Right now, we refer to our four-dimensional universe as 3 plus 1. The dimension I am going to argue for is here. I am actually adding a fourth spatial dimension, which brings time to number 5. So, since the current 3 dimensions are x, y, and z, we're going to call this fourth spatial dimension W. To illustrate how gravity can be understood by a fourth spatial dimension, we are going to revisit our two-dimensional world again. Let's say we have two circles moving through two-dimensional space at the same velocity. Their movement right now is on inertia. From a third-person view overhead, we will notice that one of the circles seems to slow down for a bit and then return to normal speed. Now the two circles are no longer side by side. What happened? Well, from our overhead view, there is no answer. But if we take this and turn it on its side, as we can see from our three-dimensional perspective, the circle's 2D world is bending into a third dimension. The reason for the change in motion is simply due to the extra distance required by adding a dimension of motion. To the circles, this bend would be imperceptible. The only way for the circle to be aware of that third dimension is by relative motion from another observer. Sound familiar? But now I have to point out the fatal flaw in this analogy because it's the same flaw with the popular bowling ball on a trampoline. When I showed you this image, you most likely thought of a hill, like what you experience in real life. In our experience, a hill has resistance on the way up and gives you kind of a boost on the way down. It is natural for us to think this way because it's the world we experience. It's what we're familiar with. However, the reason for the change in motion in this analogy is simply due to the extra distance required by adding a dimension of motion. Now don't get confused with this analogy. The hill could be represented as a bump, it could be a valley, it could be in any direction, because the direction is irrelevant. There is no direction. It's just extra space. The problem with the trampoline analogy is that we get stuck on associating it with the concept of gravity. It's familiar, but it ultimately teaches us nothing, because we end up explaining gravity with gravity.
These are examples of circular reasoning.
As we move up to our 4D reality, what we call gravity is an extremely similar phenomenon. An object traveling in a vacuum of space will appear to slow down upon entering a gravitational field to the perspective of an outside observer, not because it's falling down into a vortex, not because it's being pulled in by a plane, but simply because it's traversing additional distance in an extra dimension. Gravity, therefore, is best and most simply explained as a fourth dimension of space. Objects in a gravitational field slow down to the perspective of an external observer because they're actually traveling through more space. I believe this concept has eluded us for so long simply because it is outside of our experience. We live our entire lives in only one frame of reference, here on Earth. It's like how a fish in the ocean isn't aware of the ocean until they leave it. My goal at the end of this chapter is not just to make a case for the fourth dimension, but to teach you a new way to perceive it for yourself and a new way of looking at the world. Both of these goals start with my new analogy for gravity, a bowling ball in a box of Jello. When we put the bowling ball into the Jello, it displaces the Jello. So remember all the weird things we covered about gravity in the last chapter? Gravity is an effect, not a force. We don't fall down, the Earth pushes up. The speed of light, or c, can seem to change depending on your point of reference. Well, all these things make a whole lot more sense when space is like our Jello. When an object displaces something, it could be Jello, water, or even air, it creates pressure. The bowling ball is exerting pressure outward on the Jello, and the Jello is exerting pressure inward on the bowling ball. The Jello will also be compressed or denser around the bowling ball than it is farther away. So as we can see, this analogy lines up much more with what we're actually seeing with gravity. Instead of thinking of space-time as curved into a vortex, which again is defining gravity by gravity, fourth dimensional space is compressed while fifth dimension, or time, still remains constant. It's just that constant includes not only the three dimensions we're familiar with of motion, but also a fourth. It looks like this. If we were to create a giant ruler that stretched all the way from the surface of the Earth to the surface of the moon, and let's say we can turn gravity on and off, okay? That ruler will not move. When we turn gravity on, the ruler is still there, touching the surface of the Earth and touching the surface of the moon. We turn gravity off, the ruler is still there. The only difference is, with gravity on, now it's going to take more energy and more time to travel, again, from an outside observer, from the surface of the Earth to the moon than it would if the gravity was turned off. Keep in mind a very important principle here. Nothing can be measured without something to compare it to. We know something is 12 inches only because we know how long an inch is. We know something takes a minute because we know how long a second is. Therefore, we only know gravity changes what we currently call space-time because 3D space does not change. So, 3 dimensions of space aren't changing. A fourth dimension of space is. What I really love about this way of thinking about general relativity is that we can stop calling it space-time. I think that's one of the most confusing parts of this whole thing, is by calling it space-time, we're just admitting, time is changing, something weird's happening with space, we don't know what. With a fourth dimension of space that we acknowledge, it can just be space and time. It just really simplifies things because it clarifies the nature of time instead of being wibbly-wobbly to being a much more reliable constant. And it changes space from having to do weird things like vortexes and stuff that we continually struggle with to just having a little more room to it. So how do we become aware to perceive a fourth dimension of space? Well, the truth is you experience it every day. It's just that we happen to call the experience weight. All right, so I got 2 balls here. Sorry, 2 more balls. And this one's 12 pounds and I got this one is 6 pounds. Now, obviously 12 pound weighs more than 6 pounds. But what I'm feeling is I'm feeling the resistance, okay? The acceleration, Earth accelerating up, pushing against this pushing back on my hand, this likewise. However, just like with our elevator analogy, if I accelerate this one really fast, I can feel the same amount of resistance on my hand as this one. And that's because the displacement of fourth dimensional space is equivalent to moving in three-dimensional space. Either way, it's just distance. And we experience that distance or that acceleration either through forcing it through three-dimensional space or the fact that it's just displacing fourth dimensional space. Let's take another look at the theoretical tesseract, which again, the best we've been able to do is to draw a fourth dimensional object by taking a three-dimensional cube and adding a bunch of lines to it. The drawing itself illustrates the absurdity of trying to draw extra dimensions with the ones we are already familiar with. For perspective, this would be like a two-dimensional being drawing a cube like this. There is a hint of truth, of course, in both of these, but the reality is still far away. We're never going to understand extra dimensions by taking our three-dimensional graphs and just sticking more arrows onto it. It'll go here, maybe here, maybe here, oh, maybe it's here. The fourth dimension is not on the graph. The fourth dimension is through the graph. Just like a 3D extension on a 2D plane, the fourth dimension extends space in a way we can only perceive by relative time and motion. In truth, we already know what a tesseract looks like. It actually looks like this. This one, we have length, width, height, so 3 dimensions, but it also has weight. I mean, not much, it's wood, but it has weight. If it were just a 3-dimensional cube, it would have no weight because it's just 3 dimensions. The only place a 3-dimensional cube exists is in math or in a computer simulation. That's why video games are so weird and full of clipping errors. But let's take this for a minute and now think about it, and let's put the theoretical tesseract right here. So cube within a cube, right? The one thing our theoretical tesseract has right is that a fourth dimensional cube can be a different size in 3 dimensions than 4 dimensions. That part's correct. So is it with this. This cube takes up a certain size in 3-dimensional space, but the amount of fourth dimensional space is slightly bigger than the 3-dimensional space. That's how it has gravity, that's how it has mass. The Earth, the gravity we are experiencing is the fact that it's larger in 4 dimensions than it is in 3. Now that I've shown you how we perceive a fourth dimension and what part it plays in our reality, let me take a minute and talk about why this is so important. So up until now, I've been reasoning mainly through analogy and concepts. And I have been doing this because I want this idea to be as accessible as possible. But I also realize that for this to be a scientifically valid concept, at some point it has to show itself in the maths. So, let's rewrite general relativity. All right, so going all the way back to the beginning, this is not general relativity. It is the equation for mass-energy conversion. It is also very easy to understand, and it teaches us something amazing about our reality. All you have to know is that E equals energy, mass equals mass. You don't actually have to know C all that much, but there it is, plain as day. The simplicity of the equation itself makes very obvious what it's trying to tell us about the nature of our universe. However, this equation is also practically useless. It's oversimplified. We can't actually use this equation for most things in real life. If we wanted to actually use this in real life, we use an equation that looks a little more like this, or even this. But those are kind of hard to look at and figure out what they're trying to tell you. So, as far as education reasons goes, we stick to this. In contrast, this is Einstein's theory for general relativity. This equation is practically useful, but pedagogically useless. It's about as transparent as a brick wall. Oh yeah! Most of the kind of mind-blowing reality of what this equation is trying to teach us about our world is hidden behind these tensors in the equation. And these tensors within themselves have more equations. And so in the end, it's lots and lots of equations, really shorthanded, to the point where unless you have all the background knowledge of years of education, it's almost impossible to really understand what's going on here. Don't misunderstand me. I'm not saying the equation is wrong, except maybe this part, but that's a whole nother story. It has proven very useful for making predictions about astrological and gravitational phenomena. I'm just saying it makes it very hard to understand what is actually going on in the universe with this. Therefore, like E equals mc squared, my goal here is to rework this into an equation that is practically useless, but really good for actually understanding what is going on in our universe. In marketing, we call this setting expectations. So to do this, we will start with the basics, the Pythagorean theorem. C squared equals A squared plus B squared. C, in this case, is the hypotenuse of a right-angled triangle.
I wish I were high on hypotenuse.
It's also the distance between 2 points in two-dimensional space. This is, in physics, what we primarily use this for. Here we're going to start and we're going to count 2 dimensions, okay? 1, 2. Now, let's move on to 3 dimensions. If we want to find the distance between 2 points in 3-dimensional space, we take Pythagorean's theorem and we add another dimension. Now, we're going to change the notation here because I want to start working into thinking of distance, in space. So for here we have d squared equals x squared plus y squared plus z squared. Now we have the distance between 2 points in 3-dimensional space. Now we add 4 dimensions. And again, we're sticking to the stuff that's already established right now until we get to the 5th. In 4 dimensions, the 4th dimension we're adding is time. And for this, we use what's called Minkowski spacetime. The equation for this is ds squared equals c squared times the change in time squared minus the change in x squared minus the change in y squared minus the change in z squared. First of all, what's needed to understand here is that we are finding now not the distance between 2 points in space, we're finding the distance between 2 events in space. Event 1 happens at a point in space and time, and 2 happens at a point in space and time. The function of the equation here, the purpose of the equation, is to decide whether or not these 2 events can influence each other. Now, oftentimes this is written differently than what I have. The pluses and minuses are switched. But I've written it like this to make a point. And the point is that c, which is our speed of causality, is the bucket of time and distance that we have. The farther away these events get, the more we have to pull out of that bucket. If these events get so far apart that they extend past c, then these 2 events can't influence each other. Also in this equation, we have time. Well, time, you have c squared times change in time squared. That time is basically telling us how many buckets of c do we have. So if the events are 1 second apart, depending on the notation we use, we have 1 bucket. If we have 2 seconds apart, then we have meters per second, but then we have 2 buckets of it to pull from. This is just basically forming a simple problem of, can these events be related by causality? This also taught us about the phenomenon where we know that the more we travel through space, the less we travel through time. If this concept is new to you, you've guessed it, I have a link to an explanation in the description. So that's the reality of how we compute 4 dimensions. So now we've just counted from 2 dimensions to 4 dimensions. Again, this is all currently understood science and math here. And we're going to take the same approach to add a fifth dimension. Now, to do this, we're going to admittedly create a very hypothetical situation. See, the problem with gravity is that it's not uniform most of the time. So around massive objects, we need tensors and geodesics to figure out, all the different variations of gravity as you get closer and farther away, and the fact that the object's around, all that stuff. So to simplify all of that, what we're going to do for this fifth dimension is we're going to take events 1 and 2 from our four-dimensional situation, and we're going to put a box of gravity between them. So between events 1 and 2, it's a box of gravity with a uniform value throughout. And that will simplify things for our equation. So now all we have to do is calculate the distance between two events in space with a gravitational influence. Now, there are several ways to quantify gravity. There's gravitational force, acceleration, you have gravitational potential, and you have time dilation. However, as you can see, at this point, we're trying to figure out the distance between two events in space. So the value for gravity that's going to be most important to us for this equation is time dilation. And if you remember earlier from our dimensional concepts, higher dimensional interactions can really only be measured by relative motion or time. So time dilation is the only way we really can tangibly understand the effect of the fourth dimension in this situation. The basic equation for calculating time dilation of an object in a gravitational field is this. Now, you can fill these values with, anything. I recommend just picking something like the surface of the Earth as a very common example. So the way this works is, if I am a third-person observer outside, like our spaceship from before, and I'm looking at someone going from outside a gravitational influence to landing on the surface of Earth, that is what this equation is showing. It's showing the difference to me as a third-person observer. So we have T1, and that's going to be the new time by the person on the surface of the Earth, equals, and then we have this mess here, times the original time. And the original time is the way he would have experienced time before he went to the surface of Earth when he was out in space. So that's what these values mean. So T1 is now the new time that he is experiencing as witnessed to me as an outside observer. It looks like he's going slower. But the value we're looking for to attribute to our box of gravity is going to be the original time minus the new time. Because what we're looking for is the time difference. So the difference in time caused by gravity. So that's the value we're going to take. And we're going to take that value, and that is going to be now our new dimension, W. So now that we have the value for W, we can take it and put it into the equation we've been building on for a 5-dimensional equation, determining the distance between two events in space. That's 5 dimensions, fit neat and tidy, building all the way up from 2-dimensional Pythagorean theorem. And now we can see what's really going on here is that this fourth dimension of space is extending the time and the energy taken to traverse the same distance. Oh, and look at this. If W is greater than our delta T, we have a black hole, or in this case, a black box, because we've eaten up all the buckets of C. There's no way for one event to influence another, and there's also no way anyone can go through the box. While this equation is only feasible in our hypothetical situation here, and our box of gravity, it is not entirely detached from reality. While it's true that most of the time we're measuring gravity and looking at it, we're talking about massive objects and all the different stars and planets in space. However, this idea of quantifying gravity exclusively through time dilation or the amount of time it displaces, is exactly the same way that we test for or detect gravitational waves. But I understand, if all I'm doing is simplifying general relativity, what am I contributing? Why does it matter? Well, the answer is how we interpret math is just as important as the math itself. The way we interpret math has dramatic consequences, not just for our struggle to understand the universe, but what other equations then we justify to build off the previous one. So I want to talk a bit about how this new interpretation of gravity, thinking of it as 4 dimensions of space and 1 of time, it will impact a lot of things. But let me make one very specific example of where the way we interpret an equation go very wrong. So what I want to talk about for a minute is Gabriel's horn, otherwise known as the painter's paradox. Thought up by Evangelista Torricelli I hope I got that name right, in the 17th century. Gabriel's horn is a theoretical object with finite volume but infinite surface area. This means that a painter would be able to paint the inside of the trumpet, but never the outside. This paradox stumped mathematicians until they realized, well, hey, it's not a real object, sometimes math is weird. It's not that the math is wrong, although, to be honest, calculus is always an approximation. It can be a very accurate approximation, but it's always an approximation. Math is an attempt to describe reality. It is not reality itself. It's a way we can test our assumptions of reality, but it is not always the best way to decide reality. In this case, it just so happens that the math for volume cancels out and reduces to pi, whereas the math for surface area, again, calculus, cancels out and reduces to infinity. Now, in real life, a trumpet could have approximately the same shape, but we would have an end to it. It would end, and we would know where it ended because we could go and measure it. But the math, the way we approach it, can't tell us where that end is just by itself. This whole concept on Gabriel's horn, by the way, and the math behind it, is talked about in an excellent video by Up and Adam, which again, linked to in the description. Okay, so for some reason, we had some common sense around how to interpret Gabriel's horn, but we never seem to apply that common sense when it comes to things like black holes. The singularity in a black hole is almost the exact same situation as Gabriel's horn. By combining two perpendicular dimensions, so t and what I'm calling w, into a single plane, you get a curved surface or curved space-time, or now what I'm going to call Gabriel's hole. However, by having 4 dimensions of space and 1 of time, now these can be separated, they can be quantized, and they can be crossed. In other words, we can have limits and actually have an end to the horn. So now, if you take the 4 dimensions of space that I've just proposed, and you put those together, and you say by their combined distance, if it exceeds c, creates a perimeter by which no amount of energy can be expressed, you now have a finite black hole. So, what's inside a black hole? Stuff. Frozen in time. Just like a woolly mammoth in the Arctic. No multiverse. Sorry, Marvel.
Oh, it's funny.
No going backwards in time. Sorry, Marty.
Holy shit!
And no portal to hell. Oh, and by the way, the g in all of these equations, the g that stands for the gravitational constant, looks like this. There have always been 3 major issues we have with g. Scientists don't always like to talk about a lot. So the first of all is we have a lot of trouble measuring it. There's a lot of constants, like c, that we have been able to measure very accurately. But gravity seems to move around. The value you see here is actually more of just kind of an agreed upon, close enough. Number 2, we don't know what it represents. No one has proposed what G is. It's in all of our equations, but we don't know what's causing it or why it is what it is. Number 3, gravity is very weak compared to all the other forces that we see in nature. And that is also very interesting to scientists. With the dimensional theory I am proposing, we can now deduce that G is the total amount of fourth dimensional space displaced by matter. And as a matter of fact, it is that displacement of fourth dimensional space that causes all the other effects of gravity. This helps us understand not only gravity better, but it helps us understand mass or matter better, because keep in mind, everything's made of energy. At some point, we have to cross the line from energy into matter. And now we have a clue as to how that happens. It is energy specifically displacing fourth dimensional space, and everything else can be attributed to that displacement. This can also explain why it's so hard to measure. Objects with mass don't displace everything around it according to its size, because as we talked about in the beginning of the video, everything with matter is mostly empty space. So if I have, for example, my little tesseract, it is not displacing its size in 3 dimensions of fourth dimensional space. It is only displacing the amount of space necessary for the atomic elements to exist. That's what's actually getting displaced. Everything at a small scale is just mostly empty space. So there's not a lot of displacement going on for these atoms to exist. That is why, compared to the size of the object, the gravitational effect is extremely weak. And I'm just getting started. There are so many mysteries and things that we still don't understand that I believe can be explained by this new way of thinking of dimensions. For example,
the cumulative displacement of fourth dimensional space can help explain modified Newtonian dynamics and why it works so well at large scales, because it takes us from measuring gravity discretely to having some accumulative effect. Wave-particle duality can be explained by higher dimensional properties being observed in lower dimensions. Displacement can eliminate much of the need for dark matter or dark energy. Anti-gravity can now be better understood as a contraction of fourth dimensional space, and not antimatter falling up. Finally, we have an answer as to why hot dogs come in packages of 10 but buns come in packages of 8. We can now simplify field theory into a single field, just with more dimensions, no need for brains or pixelized space. Conservation of energy can be restored as a universal law, because what we perceive as an accelerating expanding universe can simply be explained by collective displacement of all the mass increases in the universe.
So, to wrap up, let me emphasize that this is not the end of my theory. This is the beginning of my theory. I'm not trying to sell you on 5 dimensions, but rather a whole new way to think about dimensions. With similar, albeit increasingly complex reasoning, I feel confident that I could probably get up to about 8. But none of that will matter if I can't get 5 dimensions to click. So I am pausing, partly because this has taken a lot of work, it's a lot of time, but I want to take a minute and see if just this idea of one more dimension can, if people find it illuminating before I continue. I would also be thrilled if more of you experienced physicists out there, more of you math geniuses, if this sparks an idea in your head, or if it seems to be clicking to you, I'd love for you guys to try and jump ahead of me here, or throw any ideas or suggestions back my way. But I do have one thing I'm going to throw out as a clue for what lies ahead. For the past few decades, we have been trying to explain gravity and general relativity with quantum mechanics. But what I believe is possible is that with this reinterpretation of dimensions, we can explain quantum mechanics through general relativity or dimensional relativity. I'm still workshopping the names. As I have hopefully illustrated, we don't need a quantum dimension for gravity to explain why we can't see it. We just need to adjust our awareness and examine our assumptions of what a dimension should be. I will continue to flesh out this idea. I am going to make more videos in the series, but it's going to take a while. And hopefully, in the meantime, I get some feedback and questions. I will do small follow-up videos on, if I get some great questions or anything that's worth responding to. Obviously, I'm not going to make something for that's stupid, whatever. In the meantime, you can look forward to my next chapter, which is going to be time as a spatial dimension. Thanks for taking the time to listen to me try and make sense of our universe and all its weird phenomena. Finding gravity with gravity. You have to already have gravity to understand the analogy of gravity pulling something down into a funnel to represent gravity. Oh, that was a funny way to say it.